Here we are once again. It's the Physics 2A video lecture 15, and today we're talking about oscillations. I brought in a bunch of oscillations, and there's a pretty rich phenomenology right here. So I'm going to talk a bit about each one, and then we'll actually investigate them systematically. Okay, and I'll clear the table of all this good stuff. So here, this orange mass on the end of a spring does something kind of special, because if you track it for a few seconds really, you'll see that it's spinning and oscillating up and down at the same time. And at a certain instant in time, its vertical oscillations have ceased completely right now, and the torsional oscillations took over, but now it's going back to the vertical oscillations. So that's a pretty sophisticated device, actually. Those are coupled oscillations, and that's as much as we're going to do with those. Then I have mass on a spring here. This is actually the topic of today's discussion. This would have been your lab. Mass is oscillating on springs horizontally. I could pull the masses out and it goes faster. And something of this nature was part of this week's lab. Okay. These balls on vertical spokes are kind of interesting, because you'll see we get a slower motion the taller the thing is. That one's already more rapid, and this one here is much more rapid. Okay, so what kind of an oscillation could this be? Well, this could be a skyscraper, and you could be up here on the top floor and it would be swaying in the wind like that. If you're an engineer, you'd want to know about these things. Good. And then I have some pendula. The pendulum here we'll study in great detail later in the hour. I have small pendula that seem to not do anything too thrilling, but that's a short pendulum. This is a longer pendulum, and you'll see there's a difference in the speeds. And these we'll actually introduce the proper terminology as we get going on this. Then one more interesting thing here. This pendulum will also do loops of the loop. This double pendulum here is a completely wild device, and this actually goes far beyond what we can calculate together. Nonetheless, there is a real richness of oscillatory phenomena, and we're going to have to take it systematically now. So I'm going to remove these things from view and just focus on the real basic ones. Okay. Okay, so we're going to leave these up here. This one we'll remove. These masses we can keep as well. So how are we going to tackle this systematically now? I'll demonstrate a little bit more about these before we just do the formal stuff. So here we have an interesting property that, and you can count this out. I'm going to displace this thing a little bit, a half a car length, and you can count out how long it takes to go back and forth. So once back and once back again, that is the period of oscillations. And what's interesting is if I double the initial distance here, the period is unchanged. You could actually count it out and see that I'm right on that. On the other hand, if I change the mass, so now this is much lighter, you'll see the period's also much shorter than it was before. Okay, so there's a certain oscillation. I put the mass on, the oscillation is much slower. So it depends on the mass here with the springs, but not on the amplitude. Now let's have a look at the pendulum. This is just a length of string with a mass hanging from the end, and we could count these out as well. And if we count them out for a smaller oscillation, we'd see it was actually the same pendulum, the same period. Okay. A little bit larger, still the same period. Just go ahead and count those out. 1, 2, 3. Okay, and then count these out a little with small oscillation here. 1, 2, 3, and we can even do a shorter one, a smaller amplitude. 1, 2, 3. So that's what we mean by amplitude independence. Now, I can put this mass on and double it, and you'll see if you count these out, the period has not changed. The time it takes to go back and to go across and come back again. Okay, so those are fundamental properties of these types of oscillations, and that's what we're going to focus on: the mass on the spring and the pendulum at the end of the mass at the end of a string, the pendulum. And I'll say one more thing. I don't think I'll demonstrate too much of that, but the mass at the end of a spring here, oscillating vertically, good catch, mass oscillating vertically is going to obey the same law that this horizontal oscillation obeys. Okay, so having said that, let's get started. So the first point of the presentation, I'm just going to discuss periodic motion for a moment. Periodic motion is motion that repeats itself within a certain time. So periodic motion, we're using the letter capital T for the period. So periodic motion T is the period. It's motion that repeats itself, and the unit is the second, of course. So the unit of time is the second. The unit for periodic motion is the second. Now there's another quantity called the frequency. F equals 1 over T is the frequency. So the period is in seconds, the frequency is 1 divided by seconds. So F equals 1 over second, or inverse seconds. That is the hertz. That's the hertz, okay? After a physicist named Hertz. So that's what we have for periodic motion. We have period and frequency. And an example that is not usually discussed, but I'm going to go ahead and do this anyway. An interesting example of periodic motion would be an ideal bouncing ball. So you have a ball here, you drop it, hits the ideal table, bounces right back up to the same height, and it would just bounce forever. Okay. Now that's an interesting one because we know the law of free fall. So the example, I'm going to call this the ideal bouncing ball. And we're just immediately going to do its graph. So we could drop it from a height capital A. We usually use H, but go ahead and use capital A here. Let's call this the y-axis. Let's call this the t-axis. And we know that if we just drop a ball, the law of free fall says we've got this parabolic curve there, except it rebounds. And when it rebounds, it's as though it were thrown from the ground or from the surface with this speed that it hit with, tops out and goes back again. So that would actually be a periodic motion, the ideal bouncing ball, and its period would be the time right here. And the frequency would be 1 divided by that time. Frequency is number of something per second, whereas this is the time it takes for an oscillation. Frequency is the number per second of oscillations. And I'm just gonna put T equals question mark, because that's one thing you guys could easily figure out. Because you know the law of free fall, it takes half the time to hit the ground. So half the period is the time it takes to hit the ground when you drop it. So that's actually a simple problem, okay? So anyway, that is a periodic motion. You got a period, you've got a frequency. It's not this type of periodic motion though, it's a very different type. And I'm just gonna put here as a note, here the period does depend on the amplitude or the initial height here. Period depends on amplitude, which is not the case for the ones we're going to now study in more detail. Good, so we had just the first example of periodic motion and how it would have a graph. And that's why I'm introducing that one first. But now let's go to the system with the mass on the spring. This is the one we're studying in depth. So as number 2 here on our board, mass on a spring. And then we'll remind ourselves of the whole analysis of the spring and its spring constant. So mass on a spring. And we like to discuss it being on a horizontal track. We have a spring here, and we have a mass. We're going to say no friction. And what does no friction mean for us? It always means energy is conserved, right? So no friction, we've got energy conservation. This is our x-axis. And we're going to pull the mass and release it, and it's going to go back and forth, okay? Like this one does right here. Now, why do we have 2 springs here and 1 spring up here? The reason is an ideal spring has the same behavior when you compress it as when you stretch it, whereas these springs really only do the force when you're stretching them. So we put one on each side, okay? So this is equivalent to this ideal system. And what was that spring constant? The spring constant was a force constant, so I'm going to put that up momentarily. Now, if this is the origin, I could pull my mass out to point A here and let go. Okay, so the origin, you name it where you want, pull your mass out to a distance here and release it. So that's what I'm talking about with A, which is called the amplitude. Okay, so we're going to agree to pull it here and release it and let go. And it's going to oscillate back and forth. Now this K here, K is the spring constant. And we did this on the board. Actually, I think I had a volunteer up here. We did this in lecture where we found that we have a linear restoring force. So it's the spring constant for a linear restoring force. When you have a linear restoring force, you refer to it as Hooke's law. So let's go ahead and write Hooke's law. And the force that spring exerts on the attached mass is equal to minus kx. Okay, the minus sign means it's a restoring force. It's pulling it back. If I compress it, it's pushing it forward. So that's what the minus sign means. X is linear, right? Minus kx. So that's Hooke's law. We had graphed this law earlier, and if I graph it and take the absolute value to get rid of the minus sign there, and here's my x-axis, then I'm going to get a straight line. And if I actually measure a good spring and do this in the lab, we were going to do this in our lab literally with this setup here. Okay. And then I find this linear relation. And the slope of this line, since it's a straight line, I've got the absolute value, the slope is K, and K has the units, just read it off here again, newtons per meter. Okay. And we have one more point that we're reviewing, and that is the fact that when we stretch this system, I pull this out to the amplitude, let's call that the amplitude. Okay, let's go ahead and we'll set this as my 0 right here, this marker. There's my 0. So I pull this out, and there's my amplitude. So the distance between these two markers, that's my amplitude. I let go, and it oscillates back and forth. Okay. So, good. So we have that much. Now, when I pulled it, I had to do work because I was pulling against a restoring force. So I did work. I put work into that spring. I put energy into the spring. Therefore, the spring can be said to have potential energy. So that was one thing we had also done. Potential energy of the spring, of the stretched spring. It's really just the area under this curve. Here, we've got some colors to mix it up with. If I add up all those little increments of work, it's always a little force times a little delta x, then it's the area under the curve. So potential energy to the stretched spring, area under the curve, which is say area under the straight line, and that would be potential energy equals 1/2 kx squared. We had that before, so this is just a reminder. So we've got the potential energy of the spring. I said there's no friction, so we have energy conservation. So for this system with the motion going back and forth, we have energy conservation. And that means that you could say we have 1/2 mv squared. So kinetic plus potential equals total energy. 1/2 mv squared plus 1/2 kx squared, right, equals the total energy. But the total energy is 1/2 ka squared, because that's the work I did when I pulled this thing to that initial amplitude. So I did the work, that's the total energy, and now I'm going to let go, and the energy is going to be transformed between potential and kinetic. So this is a really important expression right here. So we have almost everything here. What about Newton's law for this system? I put Newton's law up here, we'll just have all the prerequisites for further work. So Newton's law, of course, is force equals mass times acceleration. So we put down here Newton, mass times acceleration equals force, or here. I want to write it in a couple ways. So mass times acceleration is equal to minus kx. That's the specific form. Okay, this is Newton's law. This is the specific form for Hooke's law. And finally, we put it into this generic form here. A is equal to minus k over m times x. Now this one, we're going to have to keep an eye on. So it's an important expression that we'll be using. Okay, so far so good. We've got the full physics of these oscillating mass-on spring systems right there. We've got Newton's law, we've got energy conservation, we've got the force law here, we've defined the amplitude, And we already know what the period is from our prior discussion. The period is the time it takes to, if I pull it out to here, the time it takes to go over and return. Okay. Once more on this guy, the period, in fact, I'll just release it and let it return to me. So count 1001, 1002. Okay, there's my period. If I put more mass on it, go, stop. That was the period. Okay. Clearly the period was a lot longer with the masses on. So let's move on. I have to erase this whole board, but you guys have it all in front of you on your excellent video lecture notes. So now we want to discuss these things and make our way to that formula that you guys used in your lab. That's what I'm aiming at now, is to discuss how do we find the period formula, the frequency formula. Okay, so I ended with this conservation of energy idea. What I'll do is leave this picture up. This is useful. And continue on here. So we know these definitions now, and we'll be referring to this picture. Okay, so we had the conservation of energy. So from 1/2 mv squared plus 1/2 k x squared equals 1/2 k a squared for this system, we're going to solve for v. And that's pretty basic. The 1/2s cancel everywhere, and we're going to end up taking the square root. So we're going to have v equals plus minus k over m a squared minus x squared, take the square root. So there we have the velocity. I'm even going to call this v sub x in light of some developments that are about to come. So conservation of energy gives us this velocity formula. And you could say, well, why the plus and minus sign? Well, the plus sign is if we're moving in the positive direction. Minus sign means we're moving in the negative direction. So we're complete right here. So that's v sub x. Now the next thing we're going to do is the comparison to uniform circular motion. Because this is a subject here that actually requires the calculus just to work your way through it efficiently. There's a section in the text with the comparison to uniform circular motion. And I'm going to do kind of a mix of the two ideas. I'm going to take one derivative, okay? I'm allowed to take one derivative in this lecture. So we're going to compare to uniform circular motion, which we know quite a bit about. So let's go ahead and draw a circle. And we have an x-axis here. There's a y-axis. And this circle is of radius capital A. Radius capital A, the amplitude. So if we have a point here, there's our mass. That's the length A right there. And there's a theta. Okay, but I said this is uniform circular motion. So this point is going around in a counterclockwise circle at a constant speed. And because of that, we can say theta is equal to omega t. Okay, that's an angular frequency. We've talked about circular motion. It's just an angular frequency. Theta is equal to omega times t. Okay, so uniform circular motion, this is from our circular motion chapter. Theta is equal to omega t. And we know some trigonometry here. We can say that the x component, right, we've got x and y. We can say x is equal to a cosine omega t. Okay, so that's the x component of this thing just by trigonometry and uniform circular motion. So the reason we're just focusing on this x is because the projection, if you were to illuminate this thing from above, this dot would cast a shadow on the plane here, okay? The projection is gonna be found to be doing this kind of motion here, okay? One of the amazing coincidences in science. So x is a cos omega t, v sub x is equal to dx dt. Okay, I did it. We're going to take a derivative. So dx dt, the derivative of the cosine is minus of the sine, and we have a chain rule inside. The derivative of omega t is just omega. Okay, so dx dt is equal to minus omega a sine omega t. Okay, so that's v sub x. Now, what we're going to do is compare these two v sub x's. So it's got a star on this one and a star on this one. So comparing these two, we see something pretty interesting. And of course we're using this x right here. So we're going to plug this a cos omega t into this expression. We get, I'm just going to write, we find that v sub x is equal to plus minus root k over m. Pull that root k over m out. Root a squared minus the x squared is a squared cosine squared omega t. Okay. But I can pull out that amplitude a equals root k over ma. And then I'm left with 1 minus cosine squared, and that is the sine squared. And the square root of the sine squared is just equal to the sine. So I'm going to get that plus minus sine omega t. Okay, so if you like these kind of calculations, pay close attention to what I've just done here. Okay, I've discussed each step, but you could leave a little room in your notes and fill them in because that's a fun step. So we've got v sub x is root k over m a sine omega t. Okay. And now we're going to compare these, star and double star. I put them right above each other, above and below, for a reason. Okay. Because the comparison tells us what this omega is. This is the big punchline. This omega here, just from uniform circular motion, is apparently equal to root k over m. So this and omega is equal to root k over m. Put a box around that, a couple exclamation points for you. That's the important result. That's why we came here today. Okay. So we have that frequency in terms of the spring constant and the mass. Okay, so make this set of your notes, stretch them out a bit, leave yourself some room. You can make this really nice. Okay, so we're back to talking about this motion here. And we've obtained the result we were looking for. So I'm going to erase a bit more and summarize and discuss what we have here. So yeah, I'm going to erase all this stuff and put in what we now have found. We found more than you might think. Okay. Took one derivative, that's all right. Okay, so we have, let's get this up here systematically and then discuss it. So what we had was mass times acceleration equals minus kx. We then have x is equal to a cos omega t with omega equals the square root of k over m. What does that tell us about, actually, let's go ahead and put V, we found was minus omega A sine omega t. Okay, but what does this first and second line tell us about the acceleration? Acceleration is equal to minus k over m times x. A is equal to minus k over m, which is omega squared from here. So A is equal to minus omega squared cosine omega t. So that all ties together. We now have sinusoidal behavior for the position, the velocity, and the acceleration. Okay, it's possible to get all these results purely algebraically, but it takes a little longer, and I think I'm allowed to take one derivative. You guys have generally had some calculus. So we just took one derivative, got there a little faster. Good, so let's talk about this thing here. First of all, we're going to graph x as a function of t. This is our position versus time graph for these oscillations that we keep looking at here. And since it's a cosine, it's oscillatory like that. That's A, that's minus A. Yeah, where's the period? A complete oscillation could be when we released it here to when it came back exactly there, okay? So there's your period. And of course, the function cosine, where are we here? The function cosine is 2 pi periodic, right? It repeats itself when omega t goes from 0 to 2 pi. So we have, go ahead and write this way. We have for the period, like that, we have omega t is equal to 2 pi. So I'll put this in your notes because cosine is 2 pi periodic. And that gives us t is equal to 2 pi divided by omega. And so dividing by omega means we just flip this, and there's K, m over k. There's the formula you guys used this week in your lab. Okay. And by the way, this is one of the major results that I can use for some kind of problem on our exam. So when we summarize at the end of this hour, definitely going to feature this thing here. And now that we have this expression, we can see if we increase the mass, we increase the period by a square root law. So for example, if I take 4 masses, so if I had this car and I add enough mass to quadruple the car, then since I've quadrupled it, take the square root of that, I would get double the period. Okay. If I double the mass, I'd get the square root of 2 times the period, which is about 1.4. Okay, which is close to what you had on one of your problems on that lab. Okay, on the other hand, what does it mean to increase or decrease K? K is the spring constant, so if I use a stiffer spring, a stronger spring, then I'm going to have a larger denominator and I'll have a shorter period, okay, which also makes complete sense. So you can ponder this thing a bit, and you've done some examples with it. I'll give some more examples. So in particular, we've got this as our grand result. We had Hooke's law, which was essentially right here. So everything's up there. Everything's been up there. Good, so that's the mass on the spring. Let's see how much time we have for the pendulum, because our next topic is the pendulum. We're doing fine. Doing fine for time. Okay, that's our mass on the spring. We'll assign a couple of things, because I want you to be able to do some basic Hooke's law type of problems. Maybe I'll give a little example before we do the pendulum. should also say this entire subject is not just about masses on springs. It's really about anything in nature and technology that can move with very little friction and that has a linear restoring force. And linear restoring forces are all over the place. If you got a rocking chair, it has a linear restoring force. The springs on your car, you know, even this stick here, I don't know if this is going to work, but you know, if I bend this stick, it has a linear restoring force, and if I let go of it, you know, it'll have some oscillation. Okay. So everything that has a linear restoring force has this type of prototypical behavior. And in particular, that we're going to see that the pendulum also has a linear restoring force. So it also has this type of behavior. So before we do the pendulum though, let's just do an example. That's the type in these homeworks. And you start, say, with a spring, and you don't know what the K is, but you just have a spring here. I'm just going to label it K. K equals, who knows what K equals? But we attach a mass to the bottom, and then what happens is this thing stretches down to here. Okay. So we've got a mass, it stretches down to here, and now what do we have? We have a delta X, I'll call it. And then we can say, well, Fs, just magnitude-wise, don't need the minus sign right here, is equal to K delta X. X, we're changing X. And yeah, then we can say what K was. Okay. And then we can take this self-same mass, so this is first. And then the next thing is we can take this mass and put it on the track here with a different mass. But now we know the K, and then we can use the period formula that I just erased. We use the period formula to discuss its period. Or we could use a mass here to discover the K, and then we could put a different mass on here and discover the period, or predict the period. Okay. So being able to decide what the mass, what the spring constant A is pretty important. You know, if we were looking at this thing as a problem, then you could have said, okay, I've got mg here, and I've got K delta X there. And then you would have said, okay, this was a Newton law problem where K delta X minus mg is equal to 0, because net force is 0, and boom, that's how you got that. Okay? So that's a good example for this type of thing. Good, now let's move to the pendulum. The pendulum is even more important than this in a sense. This was the really abstract version, but you're more likely to set up a pendulum than you are to have a mass on a spring. Okay, because a pendulum is pretty trivial to get. And for quite a while, the pendulum clock was the most accurate timepiece in the world. Okay, it's no longer the case, but if you have a pendulum and you know its law, then you can use it to count time. Okay, so very important. So let's go ahead and discuss the pendulum. And what we'll see is we start analyzing the pendulum, and at some point we're back to this analysis that we just did. So yeah, this is a great subject. Okay, the pendulum. Once you know the law of the pendulum, you always have a clock with you. You just take a little piece of string and start counting. Well, let's have a look at this pendulum here. The idea is that we hang from some solid support a point mass at the end of the length of string L. Now, if we don't have a point mass, if we have a more extended object, we get a slightly modified result. But I'm just going to start with the simple point mass. So that's the simple pendulum. The simple L pendulum. Point mass, length of string. And what we have to do is analyze Newton's law for this thing. So this brings us back to, we want to know the force here. We know that this is mg acting on the string. We know there's a tension in this direction. We don't actually have to write it down. But if we decompose this force, then there will be a tangential component here. Okay. So let's go ahead and label this angle theta. We have this angle theta here, so that this little component that I drew, give it a different color. We practice this enough, that is going to be mg sine of the angle theta. Mg sine theta. And that is the force that is driving this pendulum along its arc. So the arc trajectory is driven by this mg sine theta. Yeah. And we've seen it goes back and forth. So now, what is Newton's law of motion for this thing? There are a couple of ways to tackle this, but I'm going to use the Newton's law for rotational motion. Let's go ahead and do that right here. So Newton tells us that I times alpha is equal to the net torque. And I'm going to make some substitutions here, and I'll write down what I did over on the right here. So the moment of inertia for a single mass on the end of a string of length L is ml squared. Okay. The angular acceleration is related to the, we go ahead and write this here. So we have the tangential acceleration equals alpha L. Now in your formula sheets before we had alpha R, but we're using a length L, not R, okay? So I can replace that alpha with A tangential divided by L, so I have tangential acceleration divided by L. You know, and that's really the linear acceleration as we go along that arc there. So what is the torque? Torque is the force times the lever arm. It is a restoring torque, because when I pull it out, it wants to go back where I pulled it from. And what is that torque going to be? Okay, the torque is going to be the force times lever arm, so we'll call it mg sine theta times L. mg sine theta times L. And here we go. We have a tangential over L. So we're going to end up with A G sine theta L. Yeah, we got that. So I alpha is equal to torque. So we have L, A tangential, masses are going to cancel. GL tangential, hold on a moment, we got to make sure we get this right. Yeah, we're good. Okay, so the first thing we can do is cancel these masses. And the second thing we're going to do is a small angle approximation. Small angles, sine of theta is approximately equal to theta. And L times theta is an arc length. L times theta is an arc length. So we will end up with m's canceling a tangential is equal to minus g over L. Times S. Okay. G over L times S. Okay. So theta L is equal to an S. That's right there. M's cancel. We've got an extra L left over here. Divide under there. A tangential G over L times S. Okay. Now what we want to do is focus on this guy and compare it. And here, erase that there. Compare this thing, this expression here, to the one we had before for the linear harmonic oscillator. So let's go ahead and put a star here. And I'll use some room right here. Compare. We had A sub x equals minus k over m x. And now we have A sub tangential is equal to minus g over L. Make that a little more clear. Minus g over L times the arc length S. Okay. So instead of going back and forth on this track here, we're going back and forth on this little arc element here. Okay, so let me go ahead and swing that. Back and forth on that little element of arc. We've got full analogy, and I need to open up a little space. This was our omega squared, now this is our new omega squared. That is the punchline. So, put a red star here and carry this over. So what we find is, from here, from equation star, we have omega is equal to the square root of g divided by L. G is just our good old gravitational acceleration. L is the length of the pendulum as shown there. And T is equal to 2 pi divided by omega by the same argument with the sinusoidal solution. So that's 2 pi root L divided by G. So this is our second main result, and I'm going to assign a bunch of problems. I think this one's even more important for our exam because we can come up with all kinds of interesting pendulum problems. So period of the pendulum. Once more, I'll write this down. Period of simple pendulum T is equal to 2 pi square root of length divided by G. Okay, fantastic. Let's demonstrate this a little bit, and then I'll tell you what kind of problems you can do. So the thing with the simple pendulum is, you just pull it back and forth and you're counting. So it comes back, there's one period, there's a second, there's a third. And you guys can time this, but if I double this mass, it's not going to change a thing about the period. Okay? Unlike the mass on the spring, right? So this doesn't change a thing about that. And you see there's no mass in our formula. Okay? What about the length dependence? It's saying that the period will be smaller, will be shorter if the length is shorter. And I can easily adjust this one here by just winding. There we go. Just wind some string up on this guy here. Enough to make it very apparent. Short pendulum has a much shorter period. So you always have a clock with you now. You just have to time any event, you just build yourself a little pendulum, count how many oscillations, take the string home and measure it, and then you'll know what the time was. Okay. So this is also the basis for really accurate timepieces. They're no longer a single mass on the end of a string. They could be, like if you've got a grandfather clock, got a bigger bob here on the end of a metal rod, and in fact, a very, very fine adjustment of the position of this bob here will change the period ever so slightly. In fact, if it's winter time, you'll have thermal contraction and the clock will run a little fast unless you adjust this thing ever so slightly. Good. So, like I said, I was going to do a summary at the very end of this just to show what all the important concepts were on one board. I think I'll end with that. We'll go back to the harmonic oscillator and the pendulum and just write down these most important formulas. I'll assign a bunch of problems with it. Actually, let's just restrict this, since the other stuff's already been on the board. Let's restrict this to the pendulum and a sample problem. So the pendulum problem, we've got a mass on the end, we've got theta. Small oscillations that I use to get my sine of theta and turn into theta means that I can't pull this out more than 15, 20 degrees if I want true accuracy. So now we have the period 2 pi root L over G. And suppose you run across a rope hanging from a ceiling somewhere and you want to know how long that rope is. You just attach a rock to the end and count the oscillations. So this formula can be solved for L. Solve for L. And what do you have? You have T over 2 pi squared equals L over G. L is equal to G, T over 2 pi, the quantity squared. Okay. So there's one example where if you measure the period of oscillations, you know what G is, now you've gotten the length. Okay. Another one would be to solve for G. Okay. You want to solve for G, you just invert this whole thing. Why would you want to solve for G? Because you want to discover what the true value of G is. If you went up to the moon, different value of G, take your pendulum, if you have an independent clock, of course, and then you can solve for G. So yeah, this formula has many uses, and what I'll do last is just show you or write down what the assignments were that I thought would be good. So the homework problems are chapter 13, and these are all easy. So I have 1, 4, and 10 with respect to springs, and I have 34, 35, and 39 regarding pendula. Okay. Good. Let's see, any last minute thoughts on all of this? Yeah, I'll bring these two pendulum examples out once again. Now that we've studied this a bit, the question is, since this is not a simple pendulum, what is its length? Okay. It's not the mass on the end of a string. It's a pretty much uniform mass, but it still obeys the pendulum law. Okay. So this is referred to as the physical pendulum. And for the physical pendulum, Let me put that up there just as a added bonus here. So that was the pendulum. I'll just do this real quickly. The physical pendulum goes back to the Newton's law with I alpha equals tau. And then what you do is you write alpha equals tau over I. And the tau is the same, it's mg d sine theta and I here. So let me do a picture with the physical pendulum, right? It's a, I'll use this space right here. Yeah, this physical pendulum's a bonus. Here's the thing, if the physical pendulum, you could say instead of a mass on the end of a stick, I just took a board, and let it oscillate, okay? Like a ruler, nailed it, through that pin and let it oscillate. So let's go ahead and just label this. We would have theta, the distance d would be the distance to the center of mass. Distance d would be the distance to the center of mass. Small angle approximation would just turn that into a theta, and the frequency omega would be equal to the square root of mg d divided by I. So if we plug in the point mass examples, we would end up with square root of mgd over md squared. And I'll leave it to you guys to prove that that gives us the same formula we just had, except instead of L, I'm using the letter D. Okay, good. That's enough. What are we going to do next time? We have one more lecture of new content, which is waves. Second half of this semester, we'll do some discussion of waves. Next week, the last lecture will be a review. Okay, so until then, just keep taking your great notes, figure it all out, turn in the homework, and see you next time.